everyone. Today we're going to be talking about binary phase diagrams and how they work with ideal solutions and being able to interpret these diagrams and use them to solve problems. So first off, we're going to be talking about ideal solutions and what ideal solutions are. So ideal solutions are usually a mixture of two or more substances that have relatively equal strength. And by equal strength, I mean they have equal forces in between each other. So the intermolecular forces in between a species and another species have equal strength in between themselves as they do each other. So species A will have equal strength in between itself, and species B will have equal strength between itself as they do between species A and B. So another thing to account for ideal solutions is that the two species have relatively equal masses, and the intermolecular forces should be similar. So a hydrophilic species and a hydrophobic species wouldn't work very well, but two hydrophilic species would work extremely well. An example of an ideal solution would be toluene and benzene. Toluene and benzene are very, very similar. They're only different in the fact that toluene has a methyl group on top of it. So their masses are the same. They're both hydrophobic, so they have relatively equal interactions between each other. So they form a relatively ideal species. A non-ideal species would be something like water and oil, where the mixture of the two don't really work well together, and the hydrophobic and hydrophilic parts of each other kind of interact with each other. And we don't really want that. That's sort of what a real solution is. And for this experiment particularly, we're just going to be focusing on ideal solutions. So for ideal solutions, we can sort of, for a liquid vapor phase between for a binary phase diagram, we can interpret it in a few different ways. Or we can interpret it in the fact that this green area up here is our liquid phase. So anything at this pressure and at this mole fraction of our species is going to be liquid phase anywhere up in this part of the graph, this green part of the graph. Specifically for this one, this is a benzene toluene graph, so this is specifically talking about the mole fraction of benzene, not toluene. So at a mole fraction of 0.6 and a pressure of 100 torr, the whole solution is just going to be liquid. Down here, this is our vapor phase, so this is our gas phase, and then this area in between is our liquid vapor phase. So when we have a mole fraction and a pressure that equals anything that's in this phase right here, we're going to have a mixture of liquid and gas phases. So we have a couple points here. So we have XA, we have ZA, and we have YA. So XA represents or I should start with ZA. ZA is the mole fraction of benzene in this solution. So for this graph particularly, it's just 0.6. So the solution itself is about 60% benzene per mole. From this, at this specific temperature, at this specific pressure, we can see that in the liquid phase, our XA, this represents the amount of liquid that is benzene. And then our YA represents the amount of gas that is benzene. And it's important to note an assumption that this graph takes into account. This only works when we are assuming constant temperature. But these graphs are very, very useful to be able to solve certain problems with these ideal solutions.
All right, as an example, we're going to look at this system involving an ideal solution of chlorobenzene and bromobenzene, where the total moles of bromobenzene is 6. And we're going to use this system. We're looking for the total moles of solution, assuming constant temperature at a given pressure, given that the mole fraction of bromobenzene is 0.600, and that the mole fraction in the vapor for bromobenzene is 0.900, and that the average composition of bromobenzene is 0.800. This is visually represented here, where we have our liquid vapor region and our mole fraction of liquid gas and our average composition. Yeah, here, 0.8. So in order to get information about the total moles of vapor and gas, well, we're going to have to use the Weaver rule, which is down here. And that relates all the information we've been given so far to the total moles of liquid and gas. Okay. So we'll pause here for a second so you can try the problem yourself.
Okay, so to set up for this problem, we're going to need two equations. We're going to need the Weaver rule that was introduced to you in the last slide. And we're also going to need a simple equation relating that the total moles of benzene exist in both the gas phase and the liquid phase. And just for the convenience, we have the given information written down and color-coded. It's also available over here, and all the blank spaces are stuff that we'll be solving as we work our way through the problem. So let's go ahead and get started. So the first step to solve this problem using these two equations is to actually rearrange the first equation, or I guess the second equation, to solve for the moles of gas. We can then input the moles of gas into the Weaver equation and go from two unknown variables down to one unknown variable. There's a Weaver equation, and we input it right here. So now this equation is set up in a way that there's only one unknown. It is the total moles of bromobenzene in liquid form. And we can plug in these values from up here. We can plug them into the equation and start to solve. So this is what it looks like after you plug in the values. We're going to do some algebraic manipulation. Right here, all we did was solve what was within the parentheses. So we did 0.8 minus 0.6 is 0.2, and then 0.9 minus 0.8 equals 0.1. As we move on, we can distribute the outside parentheses, 0.2, 0.2, and then we distribute this 0.1 into the parentheses, and we end up getting 0.6 moles minus 0.1 moles of bromobenzene in the liquid form. Some algebraic manipulation, some rearranging, and we can solve for the total moles of bromobenzene in the liquid form, which is 2.0 moles. So we can go ahead up here into our little solution box, and we can reveal the answer. Let me just make this a little smaller. So now, as you can tell, we see that we have X, Y, Z. We now have the liquid form of bromobenzene. We also have the total moles of bromobenzene. So the next step is to find the total moles of gas of bromobenzene, which we're going to do by taking the total moles minus the liquid moles equals the gas moles. And we can see that down here. Let's go ahead and find it. So we have the gas moles, which is, if you see, it's this equation written right here. Okay, we just moved it over because now we know both the total moles in liquid, and we can solve for the gas by just plugging in 6.0 minus 2.0 gives us 4.0 moles of bromobenzene in the gaseous phase. We can go ahead and reveal that in our answer box and see that we now have about half the problem worked out. And the next steps is to find the values for chlorobenzene in solution. Now keep in mind that X is the mole fraction for liquid chlorobenzene, sorry, we're over here. Y is the mole fraction for gaseous chlorobenzene, and then Z is the mole fraction of chlorobenzene in solution. Okay, so let's go ahead and see how we can solve for the total moles of liquid, which will help us, as you will see. So this equation might look a little confusing at first when you don't know what's going on. So we have the liquid mole fraction for bromobenzene equals 0.6. That means that 60% of the total liquid is bromobenzene. So we can put it in 60% of the total liquid equals bromobenzene. Okay? We can rearrange and solve for the total moles of liquid, and we get the total moles of liquid of solution is 3.33. Now, if we know the total moles of solution and we know the total liquid of bromine, we can very easily rearrange and find that the total moles of chlorine is just the whole minus the part equals the part that we desire. So 3.33 minus 2.0 equals 1.33 moles of chlorine in the liquid phase. Not total, just the liquid phase. Okay. Ooh, interesting. Let me just write this right here. So we have 1.33 moles. And we might have skipped over this a little bit, but mathematically it makes sense that if you have 0.6, if 60% of liquid is bromine, that means that 40% would be chlorine, because that is the only other species in solution. If 90% of the vapor is bromobenzene, then that means that 10% of the solution will be chlorobenzene, and if we're at a mole fraction of 0.8 bromobenzene, it will be a mole fraction of 0.2 for chlorobenzene. So let's go ahead and move on to the gas phase. We have the liquid, and we know everything that we need to know about bromobenzene, so let's go ahead and solve for gas. We're going to do it in a very similar manner that we did for liquid. If 90% of our total liquid is equal to 4 moles of bromobenzene, then we can rearrange and solve for the total moles of solution. So we can take 4.0 divided by 0.9, and we can find the total moles of solution in the gaseous phase, which is 4.44. We then do another simple rearrangement. We take total moles of gas minus the moles of bromobenzene equals the moles of chlorobenzene in the gaseous phase, and we can see that we have 0.44 moles of chlorobenzene in the gaseous phase. So the total moles of chlorobenzene will just be an addition of the liquid and the gaseous phase, which is 1.77 moles, if my math works out. All we did was 1.33 plus 0.44 equals 1.77. So in order to find the answer to our problem, we're just going to add the total moles of benzene plus the total moles of chlorine, and that will reveal our final answer of 7.77 moles total in solution.